I just did a video on the binomial theorem, but I didn't attach a section that had to do with Pascal's triangle. And I did this because Pascal's triangle, in my opinion, is one of the most beautiful things in mathematics, and I think it deserves its own video. Pascal's triangle is named for Blaise Pascal. It's a cool name, Blaise. And he was a French guy. And he entered the scene in the 17th century. What is that? He lived from 1623 to 1662. Allow me to show you guys how we can make Pascal's triangle. It starts with a 1 on the top, and on either side there goes a 1 and a 1. Then we'll add this 1 and this 1 together, and we'll get 2. But on either side of this 2, there goes a 1. Then we'll do 1 plus 2, which is 3. We'll do a 2 plus 1, which is also 3. And we'll put a 1 on either side. From here, we'll do 1 plus 3, which is 4. And then we'll do 3 plus 3, which is 6. We'll do 3 plus 1, which is 4. We'll put a 1 on either side. And these ones kind of just like go down on either side like this. Now we'll do 1 plus 4, which is 5. 4 plus 6, which is 10. 6 plus 4, which is also 10. 4 plus 1, which is 5. And then we'll continue our ones down in a similar fashion. Then at this point, we'll do 1 plus 5, which is 6. And we'll do 5 plus 10, which is 15. We'll do 10 plus 10, which is 20. 10 plus 5, which is 15. 5 plus 1, which is 6, and then we'll put a 1 on either side. At this point, we'll do 1 plus 6, which is 7, so we'll just put a 7 in between that. We'll do 6 plus 15, which is going to be 21. 21 between those two. 15 plus 20, which is going to be 35, so a 35 goes between them. 20 plus 15, which is also 35, and a 35 will go between them. 15 plus 6, which is 21. 6 plus 1, which is 7. And we'll put a 1 on either side. And we can continue this on forever, like adding the numbers on either side up with one another and then sticking their sum in between the two. Then we could keep going with that. But I think now will be our stopping point. I will draw an N up here, and I'm going to start assigning rows numbers. So this row here, this is going to be row 0. This can be row 1. This will be row 2, 3, 4, 5, 6, 7, and then this could continue. Pascal's triangle is an alternative to the binomial theorem in that it allows you to find a binomial raised to the power of n by using Pascal's triangle to calculate the coefficients of the following formula. That is, a plus b quantity raised to the power of n equals a raised to the power of n plus blank times a raised to the power of n minus 1 times b plus blank times a raised to the power of n minus 2 times b raised to the power of 2 plus whatever comes in between plus blank times a times b raised to the power of n minus 1 plus b raised to the power of n. But where these blanks are is where the coefficients go, and what determines the coefficients is the Pascal's triangle. And whatever power you're raising the binomial to, n, can be recovered by whatever row that you're looking at. In other words, n shows the row and the corresponding n shows the numbers that fill in the blanks in this formula. Let's do an example. Say that n equals 5. That is a plus b quantity raised to the 5th power. So n equals 5. Cool, I'm going to look at 5 right here. and I'm going to investigate the corresponding row. So it looks like the first coefficient is going to be 1. I got 1 times a raised to the power of n, which in this case is 5. Well, I have to find my second coefficient that goes right here in the formula. And in this case, for row 5, it's 5. So we'll do plus 5 times a raised to the power of n minus 1 times a raised to the power of n, which is set to be 5, minus 1 times b plus what? I have to find the coefficient for the third term. Well, that's no problem because I'll just use Pascal's triangle to do so. It looks like the third term is 10. And let's just see what's going on because that's the coefficient 10 times a raised to the power of n, which is said to be 5 minus 2 times b raised to the second. And so for the fourth term, we're going to look at our formula and we're going to use this ellipses as an indicator to use our mathematical intuition to follow suit with the rest of the formula. And we're going to grab the fourth coefficient, which is 10. And now there's really nothing there, but I'm going to just use pattern recognition skills to try to see, okay, well, this is going to be 10 times a raised to the fifth minus 3. I'm just going to follow the trend. And then I'm going to raise b to the third power. And so that will be the quote-unquote missing term in the formula, but I know that these last two, 1 and 2, are the only ones that are going to be applicable for the remaining coefficients. So I'm going to grab that last coefficient there, 5, and I'm going to multiply it to a times b raised to the power of 5 minus 1. Because look, the thing is if I did have a, right, and if I wanted to write it out, I could. 5 minus, if I had 5 times a raised to the power of 5 minus 4, that's the same thing as a raised to the first power, which is the same thing as a, which is what we see here. As for b, we're going to have b raised to the power of 5 minus 1 plus, well, the last coefficient is just going to be 1, so 1 times b raised to the power of n, and n is 5, so b raised to the power of 5. And honestly, I'll write in a 1. So that's what it should look like, and then I can hit it with a simplification. A plus b quantity raised to the fifth power equals a raised to the fifth power plus 5 times a raised to the fourth power times b plus 10 times a raised to the third power times b raised to the second power plus 10 times a raised to the second power times b raised to the third power plus 5 times a times b raised to the fourth power plus b raised to the fifth power. So like a real life example for an application for this could be like, let's say we have a binomial 2 times lambda plus 3 quantity raised to the fifth power. And that equals 2 times lambda quantity raised to the fifth power plus 5 times 2 times lambda quantity raised to the fourth power times 3 plus 10 times 2 times lambda quantity raised to the third power times 3 raised to the second power plus 10 times 2 times lambda quantity raised to the second times 3 raised to the third power plus 5 times 2 times lambda quantity times 3 raised to the fourth power plus 3 raised to the fifth power. And that might be an example um, that you could come across or something like that if you wanted to like plug in for the numbers in that formula because, well, this is how you derive the formula and then this is how you actually use the formula. But an alternative way to do this is like if you wanted to use the binomial theorem. The binomial theorem being a plus b quantity raised to the power of n equals the summation from k equaling 0 all the way up to n for n choose k times a raised to the power of n minus k times b raised to the power of k, such that n choose k equals n factorial over k factorial times n minus k quantity factorial. But these are two different ways that we can raise a binomial to various powers, any power you'd like. And so yeah, and so that's my video. And thank you guys so much for watching, and I hope you have a good day.